In this lecture, I want to talk about limits at infinity, and what we mean by this is the end behavior of a function. What happens as we go, if you think about the graph, as we go all the way out to the right. So let's go ahead and just draw a quick sketch of this function, 1 over x. So it looks like this over here, and like this over here. So as we go farther and farther out on the x-axis here, what does the function seem to do? So if we think about this, we could also make a table, but I think we can just think about, x is getting larger and larger, and 1 is staying 1. So if you take 1 and divide it by 10, you get 1/10, and divide by 100, you get 1/100th, by 1,000, you get 1,000th, and so on. So on one hand, it's clear that it's getting smaller and smaller. The question is, can it ever equal 0? And the answer would be no, right? Because the only way a fraction could equal 0 is if the numerator equals 0, and this numerator will never be 0. But if we recall what we mean by limit, what we mean is what value can we get arbitrarily close to. Even if we never reach that value, we can get as close to that value as we want just by taking x values closer and closer, or in this case, larger and larger. So in this case, the limit is 0. Even though the function will never equal 0, what this means is that we can make this function as close to 0 as we like by taking x large enough. And we see this with the graph. So we have, we talked about vertical asymptotes. In this case, we have a horizontal asymptote, right? And it's going to be y equals 0, which is the x-axis. So as you go, we can actually have a horizontal asymptote to the right or to the left. So in this case, since we're looking at as x goes to infinity, we're looking at a horizontal asymptote as we go to the right. It would be the x-axis. So it's kind of, again, it's the end behavior. What does this function how does it seem to behave as x gets larger and larger and larger? We can also look at it to the left. We could take the limit as x goes to negative infinity of 1 over x. So here, we're dividing by negative values. But again, if I divide by negative 10, I get negative 1/10. Divide by negative 100, I get negative 100th, and so on. So we can see that the same type of behavior is going to happen going to the left, that this will get closer and closer to 0 but never actually reach 0. So we have to remember what a limit means. It doesn't mean that this function can equal 0 to the right or to the left, just that we can get as close to 0, we can make the function as close to 0 as we want by picking x values sufficiently large in this case or sufficiently small in this case. So let's just take a look at another quick example before we generalize. What if I wanted to take the limit as x goes to infinity of 1 over x squared? All right, now that graph, because I have an x squared, and actually we want to look at both of these, but since I have an x squared, it doesn't matter what value I choose for x. 1 over x squared will always be positive, right? Because, whoops, this should be negative down here. So here I'm looking on this side over here, and at negative infinity I'm looking over here on the left, on the right, yeah, the left side. So as it turns out, if you were to graph this, you would see that you would get something that looks like this. And again, they're always positive, because whether I choose x to be positive or x to be negative, when I square it I get a positive number, and 1 divided by a positive number is a positive number. And for the same reasoning that I discussed up here, you can see that this is going to be 0, and this will also be 0. So y equals 0 is a horizontal asymptote both to the right and to the left for this function. Because again, we are actually this will go to 0 even faster. I should say it would tend towards 0 even faster, right? Because now if I put in 10 and square it, then I get 100. So already at 10 I'm at 100th. Up here it took me, I had to go out to 100 to get to 100th. So this will actually go towards 0. It'll get very close to the x-axis very quickly. But again, we're talking about end behavior, so it's going to be the same in both cases. So, to generalize what's going on here, we can say something of the form c over x to the r. So c is some constant, and r is a positive number. All right. So in this case, c was 1 and r was 1. In this case, c was 1 and r was 2. So anything of this form, if we take the limit as x goes to infinity, c over x to the r, we're going to get 0. All right, and likewise if we go to negative infinity. All right, so it doesn't matter what c is. All right, because even if it were 100 or 1,000 or 1,000,000, if you take x large enough, the point is it's constant. It's not moving. If it's 1,000,000, it's going to stay 1,000,000. I can just keep picking larger and larger and larger values of x, and that will make this get closer and closer and closer to 0. So let's just see a quick example of something a little bit different. So if we take the limit as x goes to infinity of the function 4 plus 3 over x. So one thing I want to point out here is that these limits at infinity behave, they follow the same properties as the limits that we've already been studying. So I could rewrite this as the limit as x goes to infinity of 4 plus the limit as x goes to infinity of 3 over x. So remember, these limits, we can write the limit of a sum as the sum of the limits so long as each of those limits exist. That's what we're going to investigate now. But 4 is just a horizontal line at y equals 4. So no matter how far I go out on the x-axis, it's still going to be 4. So that's going to equal 4. And this, we just said, here's the general form. But even if we look back at, that's just, instead of 1 over x, we have 3 over x. As x gets larger and larger and larger, that will tend to 0. So the limit here will equal 4. All right? Okay, let's look at some different types of examples. I want to look at 3 different cases. So let's look at the limit as x goes to infinity of x squared plus 3 over 2x cubed minus 1. And then I also want to look at the limit as x goes to infinity of x squared plus 3 over 2x squared minus 1. So I'm going to change the cubed to a squared. And then finally the limit as x goes to infinity of x squared plus 3 over 2x minus 1. So in this case it's 2x cubed, 2x squared, and here just 2x. So if we look at these individually, x squared plus 3, so as x goes to infinity, this is going to blow up to infinity, right? Because that's what x squared does. Adding 3 to it isn't going to affect it because that's constant, so we really just look at this. And then likewise here, 2x cubed, as x gets larger and larger, 2x cubed blows up to infinity. So they both go to infinity. So I would end up with something of the form infinity over infinity. But the question is, as we get, if x gets large enough, does one of these grow faster than the other? So one way to, and we can see that it's likely that the denominator is going to grow faster, right? Because x cubed, again, so for example, if we put in something like 10 here, so when x equals 10, I would have, up here I would have 103, and down here I would have, what, 2,000 minus 1, so 1,999. So that's already about a tenth, right? So it looks like if I were, if I were to keep picking larger and larger values, maybe, because if we just put in 1 right off the bat, we get what, 4 over negative 1, negative 4. And if we put in 0, we're at 3 over negative 1. If we put in 2, we're at, what, 7 over, what would that be? 8, 16, 7 over 15 at 1/2. So Anyways, we can see that some things are going on when x is close to 0, but here, as x gets larger and larger, it seems to be getting closer. It seems like the denominator is growing faster. So one way to see that is, let's just take this thing, x squared plus 3 over 2x cubed minus 1. And I'm going to multiply by 1 over x cubed over 1 over x cubed. What I'm essentially doing is I'm going to divide each of these terms by x cubed. I can divide by a function over itself, because that's equivalent to 1, and I should get something that's algebraically equivalent to what I started with. So I would end up with x squared times 1 over x cubed would just leave me with 1 over x. And then 3 times 1 over x cubed, that gives me 3 over x cubed. So if I multiply 2x cubed times 1 over x cubed, the x cubes cancel, I'm just left with 2. And then minus 1, I'm just going to end up with minus 1 over x cubed. Now if I take the limit as x goes to infinity, I already know that this goes to 0, this goes to 0, and this goes to 0 by this property up here that we've just summarized. All right? So that's going to be 0 plus 0 over 2 minus 0, which just equals 0. The important thing here is that my denominator wasn't 0. Otherwise, I would have had 0 over 0, and I can't assume that that equals 0. That's an indeterminate form. Okay. So the moral of the story here is that if the degree of the denominator is larger than the degree of the numerator, then this is going to tend to 0. It's going to be something along these lines, where the denominator is growing faster than the numerator. And as a result, as x gets really large, then this term is going to dominate. And it's going to go to infinity in the denominator, making the whole thing tend towards 0. All right, let's look at the next example. So likewise, x squared plus 3, 2x squared minus 1, as x goes to infinity, this looks like it's going to go to infinity over infinity. We could play around with a table, but let's just try this technique that we did here. Here what we did is we divided by the largest power of x in the whole expression. Let's do the same thing here. So if I have x squared plus 3 over 2x squared minus 1, the largest power of x is x squared, so let's multiply by 1 over x squared over 1 over x squared. All right? And because that's going to give us things that look like this, and then we can use this property to see that those would go to 0. So x squared times 1 over x squared is just 1. And then I have plus 3 over x squared. And then 2x squared times 1 over x squared. The x squareds cancel. I'm left with 2. And then minus 1 over x squared. Now, again, this is equivalent, algebraically equivalent to what I started with. I take the limit as x goes to infinity. I know that this goes to 0, as does this. And I'm left with 1/2. All right? So, if we had done a table, we would also have seen that these values for larger and larger values of x get closer and closer to 1/2. So the moral of the story here is if the largest power of x in the numerator and the denominator are the same, this 2 here, if they're the same, then this is going to go to the ratio of the leading coefficients. In other words, the coefficient of x squared up here, we don't write it, but we understand it to be 1, and down here it was 2. The big idea here is that both of these are growing at the same rate. The 3 and the negative and the minus 1, they don't count for much when x gets really large. They're making very little difference to the overall value of this expression. And so these terms tend to dominate when x gets really large. And they're going to grow at the same rate. So the whole thing you will have a horizontal asymptote at y equals 1/2. So as we go out to the right on this graph, it will kind of settle. It won't necessarily reach that point, but it'll settle near 1/2. Likewise here, if we have something like this where the largest power is in the denominator, then this will settle on y equals 0. That will be our horizontal asymptote. So after investigating these two, it might be a little bit easier to see what's going to happen here, because what we have here, where the largest power is in the numerator instead of the denominator, so here we have an x squared, but here we only have an x, then you would think that kind of the opposite of what happened here is what, so you see here, because the denominator grew much faster, the whole thing went to 0. Here the numerator is going to grow much faster than the denominator for large values of x. So, if we just look at them separately, that looks like it's going to go to infinity, just like it has up here. The denominator will also go to infinity. So, just looking at it separately, it looks like we have this infinity over infinity thing, which we can't really tell anything from. But if we were to apply the same technique that we were doing before, so we take this largest power of x and divide everything by that. So I'm multiplying by x squared plus 3 over 2x minus 1 times 1 over x squared over 1 over x squared. That's going to leave me with 1 plus 3 over x squared. And down here, 2x over x squared leaves me with 2 over x minus 1 over x squared. So these already, we know this will go to 0, this will go to 0, this is tending to 0. So the denominator is going to 0 while the numerator is going to 1. And so we're taking 1, dividing it by smaller and smaller and smaller numbers. This is going to go to infinity. So when the largest power is in the numerator, the whole thing tends to infinity. When they're the same, it tends to the ratio of the leading coefficients, and when the largest power is in the denominator, it's going to tend towards 0 in the long run. Okay, so that's for rational expressions that you have not just a constant, but you have the ratio of two functions, of two polynomials. Just a couple more examples to look at. Let's look at something like sine of x over x, and we want to take the limit as x goes to infinity. Well, we know, if we look at this, we know that sine just kind of bounces back and forth, right, as we go to infinity from -1 to 1. So it's going to go up and come down and go up and come down, and it's going to just continue like that forever. All right. So we know that sine of x is always less than or equal to 1 and greater than or equal to -1. But x is going to grow. So as x gets larger and larger and larger, these will get smaller and smaller and smaller. So ultimately what's going to happen here, we have what's called kind of a damping factor. So if we look at what this looks like, well, at 0 it's undefined, and actually it's going to start up near 1. We've already investigated this function. It starts up near 1, but then it gets closer and closer, right? So it crosses. It's going to have the same period, but it's going to, how much it comes off of the x-axis will get smaller and smaller because we're dividing by larger and larger numbers. So in this case, it's going to tend towards 0. I'm not going to prove that, but I want you to have some intuition. You kind of think about what's going on here. Well, sine x is periodic. It always stays between 1 and -1. If we divide, another way to think about this is we could use the squeeze theorem. We could divide everything by x. All right, and if we take the limit as x goes to infinity, well, then that goes to 0, and this goes to 0. So this limit in the middle, what we have is that the limit of sine x over x as x goes to infinity is going to be between 0 and 0, which means that it has to also equal 0. So that would be a more analytic approach. Whoops, that's kind of a messy sine x. All right, let's look at another trig example. How about cosine of 1 over x? Take the limit as x goes to infinity. Well, the only thing that's moving here is what's inside here, and we already know that the limit as x goes to infinity of 1 over x equals 0. Again, we're not saying that 1 over x equals 0, we're just saying that it gets arbitrarily close to 0 as x gets larger and larger. So if that's what happens here, then we can say, well, what's the cosine of 0? Because that's the limit, and the cosine of 0 is 1. So the limit as x goes to infinity of the cosine of 1 over x would be 1. It doesn't mean that this function will equal 1 at any point, because this will never actually get to 0, but we know that the limit of this is 0, so cosine of that would be 1. So the limit of the whole function equals 1. All right, just two more functions that I want to talk about here. I want to look at the limit as x goes to infinity of e to the x, and the limit as x goes to infinity of e to the negative x. Right? So let me come down here and just make two. So e to the x, we should know by now, it's going to go through the point 0, 1, and it grows exponentially fast. So there's e to the x. And it's an increasing function, whereas e to the negative x, also when x equals 0, it also equals 1, and it is symmetric about the y-axis. With e to the x, it looks like this. Here's e to the negative x. All right, so looking at this, we can tell that the limit as x goes to infinity e to the x, well, we're taking e to larger and larger and larger powers. It grows exponentially fast, so this is going to be infinity. On the other hand, e to the negative x, well, that's equal to 1 over e to the x. And as e to the x, we just said, as e to the x, as x goes to infinity, e to the x goes to infinity, so I'm taking 1, dividing it by larger and larger numbers. So we can see also by this graph, that is going to tend to 0 for arbitrarily large values of x. Then what about negative infinity? If we go the other direction, then the limit as x goes to negative infinity of e to the x, all right, well, that's, I'm putting in negative values for x, this is going to just shrink very quickly to 0, whereas over here, if we go to the left, x goes to negative infinity of e to the negative x, this is going to grow very quickly. So we can kind of see this also from this symmetry. As we go this way, e to the x goes to 0, and this one goes to infinity. If we go to the right, e to the x goes to infinity, and e to the negative x goes towards 0. One last example with an e to the x in it. And it's a unique example because it's a case where we have a different horizontal asymptote to the left and to the right. We started off with an example at the beginning where, a couple examples where the horizontal asymptote was y equals 0 whether you went to the right or to the left, both here and here. It was y equals 0 in both cases. So let's look at an example using e to the x. So it's limit as x goes to infinity of 3 over 1 plus 2 e to the x. Well, the only thing that's going to change as x goes to infinity is this term right here, right? The 3 and the 1 stay the same. So we can rewrite this as 3 over 1 plus the limit as x goes to infinity of 2 e to the x. All right, now we could bring that 2 out front, and then we can just refer back to what we were just looking at, right? So if we wanted to kind of look at this a little bit closer, we could rewrite this whole thing as 2 times the limit as x goes to infinity of e to the x, and we know that that limit equals infinity, right? So that's an infinite limit. We just have to remember what that means. It doesn't mean that infinity is a number. It means that this grows without bound as x gets larger and larger. So the bottom line here is that this whole thing right here is growing and growing and growing, and adding 1 to it isn't going to do much when this thing gets really large. And 3 stays the same. So 3 is being divided by larger and larger and larger numbers, so the whole thing is going to tend to 0. So as we go to the right, then we will have a horizontal asymptote of y equals 0. Let's look at what happens when we go to the left. All right, so we have the same function, 1 plus 2 e to the x, and just like we did up here, we can rewrite that. Since the 3 and the 1 are constant, the only thing that's going to move is this piece right here. which we could write, just as we did here, we could rewrite it as 2 times the limit as x goes to negative infinity of e to the x. And back here we said as x goes to negative infinity, if we go this way, e to the x tends to 0. So this limit equals 2, well, it's going to be 2 times 0, so the whole thing is going to be 0. So that's this limit right here is 0. So we're left with 3 over 1 plus 0, which equals 3. Again, it's the limit. It's not saying the function will ever achieve the value 3, but it will get arbitrarily close to 3 as we pick x values smaller and smaller and smaller. So here we have a horizontal asymptote of y equals 3. So our graph would look something like, well, we know, let's see, if this is x is 0, then I'm going to, e to the 0 is 1, 2 times 1 is 2, plus 1 is 3. So I know I'm going to go through the point y equals 1, 2, 3. I will have a horizontal asymptote here. So this thing is going to kind of come like this, and then it's going to get close to the x-axis because of this horizontal asymptote to the right. So we have to the left a horizontal asymptote of y equals 3, to the right a horizontal asymptote of y equals 0. All right, so that is just a look at limits infinity of a few different types of functions and what that means, how we can compute them.